All right, I'm Mike Spertus, and I'm going to talk about how to OO in C++. So here's what we're going to discuss. When faced with OO problems, many C++ programmers have the perception that they need to use inheritance and virtual functions to model that kind of behavior, but that's far from the only way to do it in C++. So these OO techniques are often a better choice in practical programs, and I'm going to cover 3 approaches that I come to time and time again that seem to cover most of my use cases. So first of all, the familiar inheritance and virtual functions, then concept-based approach, and a variant-based approach as well. Now, to begin with, I've been saying, what is OO? Well, spoiler, it's object orientation. Okay, but what is object orientation? Spoiler, nobody knows, right? So here's a quote from Benjamin Pierce's Types in Programming Languages textbook. Most arguments about what is the essence of do more to reveal the prejudices of the participants than to uncover any objective truth about the topic of discussion. Attempts to define the term object-oriented precisely are no exception. So what are we going to do? We'll just take it as face value. When I say object-oriented, I mean oriented around objects. Whenever we need to do some operation, we ask an object to do it for us, say by calling a method on that object, and what it and how the object does that is none of our business. So we appeal to objects to do all our operations. Now, how are methods defined in C++? Well, they're typically defined as part of the object's class. So here we have a class A. It is a method foo and a method bar. The first one returns the string foo. The second one returns the string bar. They're declared a little differently, but let's not worry about that for the moment. But if I create an object foobar of type A and call foobar.foo, it'll give me a foo, and foobar.bar, it'll give me a bar. So the print statement on the bottom will print foobar. So there was something I kind of slipped under the rug, though, in what I just said. We said it's the object's class that decides how the object performs operations. But what is the object's class? And I think this is what gets to the heart of object orientation, because any expression in C++ is 2 different types. The first is the type of the expression, as it's understood by the compiler as a C++ expression, and this is called the static or the compile time type, where the second type is the type of the actual object in memory. And these are not necessarily the same thing, primarily due to inheritance. And when the same object has one runtime type and one compile time type, that's typically called polymorphism. And in this case, well, which class's method is used when you perform an operation on that object? Now, here's the philosophy most languages take, which is the language chooses. And most languages always use either the runtime type or the compile time type. So Java describes itself as an object-oriented language. Therefore, it always uses the runtime type, the type of the actual object in memory at runtime. On the other hand, C does not describe itself as object-oriented, so it always uses the static type, which is the type of the expression at compile time. Okay, what's the philosophy of C++? Anybody? Yeah, the programmer chooses. Since both are useful, C++ supports each. And non-virtual methods use the static type. Virtual methods use the dynamic type of the object. And as usual, this makes C++ a little more complicated and a lot more powerful. So we want to look at that. So first, let's just look at a little example. It may be hard to read on this slide to make sure we understand the difference between a virtual method and a non-virtual method, but I'll talk it out. So here we have a struct animal with a method named V, method named F that prints animals F, and a virtual method named G that prints animals G. And then we have a struct gorilla that inherits from animal that has an F, G, and an H, each of which prints gorillas F, G, or H. We're not simulating actual gorillas here. We're just trying to recognize which class is being called. So here I have a gorilla object G, and now I have an animal reference A that refers to that G. So if I call A.F, is that going to call animals F or gorillas F? Right, animals F, because F is not virtual, which means it uses the type of the expression A, and A is an animal reference. But what if I call A.G? Gorilla, right. Because G is virtual, it's going to use the type of the actual object in memory to determine which operation to use. What happens if I do A.H? Well, that's ill-formed. A has no H method. And if I call GF, GG, or GH, it's going to print gorillas F, G, and H because all the types of G are gorilla. So the first question is, we don't want to be needlessly complicated. Why not always use virtual methods? Object-oriented languages like Java, all methods are virtual, and I'll use OO without quotation marks to refer to this familiar OO style of using inheritance in virtuals. And is there any reason not to make all of your methods virtual? So let's take a look. Well, one reason is performance. And you've probably heard a lot of people telling you that virtual methods are free, right? They only have single indirection. Compilers are really good at, or processors are really good at branch prediction and the like. And this is true most of the time, but it's an oversimplification. And let's look at an example of that. So here I have a program that creates an object A, calls its F method 100 million times, and it keeps incrementing the second argument to F. And, keeps incrementing the first argument to F. And then it tells us how long the whole thing took. And if we look, the method F is virtual. Let's try running this program and timing it.
With or without optimization?
Well, you always want to do benchmarking with optimization.
This was my point.
So I was very careful to do a release build here that has a appropriate level of optimization. Let's go ahead and run it. Took a little over half a second. Okay, but now what's the overhead of doing lookup at runtime, what method to call? So let's get rid of the word virtual. Go ahead, run it again, and it takes about half a second to run. Right, it's within the standard error of the measurement. So the people who tell you don't worry about the cost of virtual functions sound like they're right. But now let's change it to a very slight change to this. Now we're going to increment the second argument each time through the loop. Let's build this, we'll run it, and it takes about half a second to run. But it's virtual. Let's do a non-virtual method. It took 1/30 of a second to run. So it's over 10 times faster. So what happened? Any ideas? Right? Now the program got way faster without virtual methods. You can see the F method here.
Is it because of the static cast?
No, the static cast isn't a problem, but what happens here is when we're incrementing the second argument, it has to calculate the log differently every time through the loop. If we're incrementing the first object, you only need to do this expensive logarithm calculation once because it never changes, and the compiler can't really tell that because it doesn't know what's going to be called each time through the loop, right? So this tells us that the main performance cost of virtual functions is not the actual cost of doing the runtime calculation, but it's the way it obscures the behavior of the code from the compiler's optimization, right? And the compiler doesn't know what type of code is going to be run because it's not based on the compile time type. It's based on the runtime type, which is not known at runtime. So this usually isn't significant, but this case is good to understand. In fact, the more virtual functions you use, the less well your compiler can understand your code to optimize it. Here's another problem with virtuals: polar bears, right? So Java programs use 50% more energy than C++ programs, right? Here's a link to a paper on it. And while it's true that modern Java JITs use advanced devirtualization techniques, basing all dispatching on runtime types is presumably a big part of the reason why. Now, you might say, well, you know what, if my program runs a few percent slower, well, okay, it doesn't matter in the big picture of things, but over billions and billions of calls, you're going to melt a lot of ice, right? So if virtual functions use more carbon than non-virtual functions, and even if it's a small number, computers call them a lot, so it can add up. Another reason is interoperability. Code that needs to interoperate with other languages needs data type with a fixed layout in memory. In fact, C++ provides an is-standard layout type trait to check this. And the presence of any virtual methods in your class mean you no longer have control over how it's laid out in memory, because the compiler has to put some secret runtime type discovery data that's not visible to you, but is actually stored inside the object's memory. Another reason, this is something that people have only recently, I think, come to really understand, which is verifiability. Since virtual methods calls are not dispatched at runtime, it's much harder, not just for compilers to understand what will be run and optimize it, but also code coverage tools, static analyzers, model checkers, automated reasoning tools, and the like have to go with much less useful information for them to give good results when virtual methods are in the picture. Here's another reason. So if I'm using inheritance in virtual functions, well, a class needs to inherit from every possible thing that it might want to redefine the behavior of at runtime. So if you're familiar with the solid principles of object-oriented best practices, the interface segregation principle says many client-specific interfaces are better than one general-purpose interface. And the solid principles are pretty good principles. If you want to hear a lot more of them, Tony Van Eerd, who I think spoke here yesterday, has a great talk on the solid principles. All his talks are great. So this means you got to have everything inherit from all kinds of things, and you quickly get a messy, unmaintainable spaghetti inheritance hierarchy in practice. And, you know, we'll make that more concrete as we go on. So here's another problem with virtuals, which is no client-side extensibility. So suppose you're writing a game using these animal classes, and the animal class hierarchy you got from an animal library, the Boost animal library, or something like that. And now, for your game, you wish each animal had a virtual hit points method. But of course, they don't, because the designer of that hierarchy doesn't know about your app. And as a result, you're stuck with the virtual methods they put in the class. And this happens a lot, right? There's a solid principle for this too. It's called the open-close principle. You want to extend the class's behavior. Open means you want to add a hit points virtual method, but you don't want to modify the classes. Keep them closed. Well, how do you resolve that? So, what are the best practices for virtual methods, right? Usually it's fine to make methods virtual. The performance cost is almost always minimal, and the availability of runtime dispatch is powerful in object-oriented code. But don't use virtual functions if there's no reason to use them, because gratuitous use of virtual functions can impede your compiler's ability to optimize your code, unpredictably modify memory layout, impede program analysis and automated reasoning tools, lead to unmaintainable spaghetti inheritance hierarchy, fail to deliver client-side extensibility, and of course, kill polar bears. So, it's worth looking at, are there other ways to solve these kinds of problems without using virtual methods? And in fact, templates and object orientation can solve many of the same problems. And here's a quote from Bjarne saying generic programming should just be normal programming. So object orientation templates can be used for many of the same problems, with template inference playing the same role as virtual dispatch does. Let's consider a real-world example. Well, suppose C++ didn't have mutexes, right? You're like, that's crazy, but we didn't have them until 2011, right? So suppose you had been tasked with adding mutexes and threading in C++ 11. Well, how would we go about designing them? Turns out, I know none of you will believe this, but some languages already had support for threading before 2011. Okay? So you'd go and do some research and find that an obscure language called Java, in fact, had mutexes. So you look at how it does it, and it uses inheritance and virtual methods, right? So they do it something like this. I'll write it C++ style and with RAII. But they have an abstract class called lockable that is pure virtual lock and unlock methods. And then you implement them in your mutex class, which inherits from lockable and overrides those methods. And to use it, you have a lock guard whose constructor locks the lockable and destructor unlocks the lockable, and it has a reference to the actual mutex in there. And because these methods are virtual, it will use the runtime type, meaning the type of the actual mutex. And it'll call mutexes lock and unlock rather than the non-existent lock and unlock and lockable. And how would you use this code? Well, you'd write something like this. You have a function. When you enter the critical section, you get a lock guard on it. You do stuff, and when you leave the function, the lock's released. You're out of the critical section. This is exactly how C++ code looks. So is that how we did locks in C++? No, we did not, right? That is not how C++ mutexes work. They do not inherit from a lockable base class. And the C++ committee decided to use templates instead of virtual overrides. And since mutexes are frequently used in performance critical code, this seems like a pretty solid choice to me. So let's take a look. Well, here our C++ mutex has a lock and an unlock method, but it's not virtual, and I don't need to inherit from anything. And now lockguard is no longer a struct, but it's a struct template. And it has a reference to the actual type of the mutex. So when it calls lock and unlock, it'll call the real methods of the mutex, and the client code looks exactly the same as before, especially starting with C++ 17, where class template argument deduction deduces the template arguments for lockguard. So we get exactly the behavior we want without requiring as rigid of inheriting and without running everything through a virtual method. And concepts make this even better, right? So in the spirit of Bjarne's quote, new C++ features like C++20 concepts were intentionally designed to be familiar to users of normal object-oriented code. Let's give an example of how we would convert some virtual inheritance-based object orientation to concept-based programs that can do many of the same things. So here's the traditional thing you learn in your object-oriented programming class. We have our struct animal, and it has name and eats methods that are both virtual, and cat overrides them. So now when I say unique putter animal A equals make unique angle brackets cat, and now this prints a cat eats mice because a arrow name uses the type of the actual object, which was a cat, and that's cat, and so forth, right? Now, the question is, do we really need to use inheritance and virtuals to write in this style? Well, not really. In fact, it's almost easier to do this. So here, I'll just have a cat struct. It has an eats method and a names method. And in main, I say auto A equals cat, and I print, again, a cat eats mice. It works just the same, right? Now, is it as good? It's a lot simpler, but simpler isn't always better, right? In particular, looking at this, you don't really have any indication that A is an animal in this. So it's very hard to understand what your expectations about A are, right? So A could have the type house or int, and we might not find out that it was an inappropriate type until much later, right? Meaning a million lines away. I don't mean at runtime. You'll still catch it at compile time. But what we really want is a way to codify our expectations for A without the overhead and brittleness of forcing it to inherit from an animal base class. And that is what concepts do. They play an analogous role for generic programming to the one that base classes play for object-oriented programming. A concept explains what operations a type supports. So here we're going to create an animal concept, and T is an animal if it satisfies the requirement that an object A of type T has an eats method that's convertible to string and a name method that's convertible to string. So now we can ensure that A represents an animal and is not a house or an int, because I modify my code now to say animal auto A equals cat, and that will only do the auto inference if the type satisfies the animal concept. Obviously, there's a lot to concepts, and this isn't a talk on how you define concepts and all of that, but I think the motivating idea should still come through, even if you haven't used concepts. And now, again, our cat still eats mice, and this code will tell you as soon as you initialize A if A is not something that has animal behavior. And we can have a godbolt here for doing this, which of course is not popping up. There it is. Okay, so first, I'll show the client code that uses these types. Well, it's basically the same in each. Maybe I'll make the type a little bigger, right? In fact, the animal auto A equals CAD is a little simpler than unique putter animal A equals make unique of cat. And we'll come to that later. But I can use them, either one, to support this use case. And if you look at the code up there, you see in one case I implement it with virtuals and overrides. In the other case, I have an animal concept and I define a CAD in such a way that it satisfies the animal concept. So, generic programming should just be normal programming. Bjarne was right. Okay, that's not surprising, right? So let's compare these. Well, first, the performance is better. Now, you might think it's because we avoided the virtual method, but while if you go overboard with virtuals, that can gum up your performance, but for the most part, it's okay. The really big difference is we were able to create our cat on the stack. I never needed to use make unique to do a memory allocation out of the heap, right? So, and a memory allocation typically takes hundreds of machine instructions, right? There's no inheritance, so it's easier to adapt classes to our code without risking having to do a million different things to inherit from, right? On the other hand, while it doesn't lose static type safety, it weakens it a little bit, right? So Pac-Man isn't an animal, but eats and has a name. A more serious problem is sometimes you really can't know at compile time, right? So let's say we wanted to create a zoo of animals. Well, I could say set unique putter angle brackets animal in the virtual inheritance case, but I can't say give me a set of animals in the concept case, because in a set, everything needs to have the exact same type, right? Or a vector or anything else. You can't have a set angle bracket some concept, because now it's a set cat, dog. What's your favorite animal?
I don't know.
Okay. Set cat, dog then.
Go with cat.
Doesn't have one. So what does this mean for practice? Well, there's usually a choice between base classes and virtuals in templates and concepts. And as we'll see below, these aren't the only options. So let's try to understand some of these problems a little better. I want to return to this client-side extensibility problem. Now, suppose you're using this animal hierarchy and you really wish they had a virtual hit points method. But the class designer doesn't know you're writing a game, so they didn't put one in. And even if they were your classes, you probably don't want to clutter up your animal classes with general interface with the particulars of every application that uses them. So it doesn't even feel like they belong in there. Now, one way to address this is with something called the visitor pattern, and this makes your class inheritance hierarchies extensible. So how would we add our hit points method? Okay. Well, we need to do two things. And by we, I mean the class designer, right? So if they didn't design the animal hierarchy for extensibility, you're out of luck. But what they can do is create an animal visitor class that can be overridden, that has a visit method that takes a cat reference and a visit method that takes a dog reference. And then they add an accept method to each class in the hierarchy that accepts an animal visitor, and in each particular animal, they override it to visit with that kind of animal. And then overload resolution will call the right visit method from the visitor. So, assuming the class hierarchy designer put in this extensibility mechanism, well, now I can create a hit point visitor by inheriting from animal visitor, and the dog sets the hit points to 10, and the cat sets the hit point to 12, and now I can use the hit point visitor to, that should say HP, not years, right, to set the hit points based on the actual type of the animal object, the runtime type. So basically, I defined in my visitor what I wished all the virtual methods were in each animal type. And now we can see if the animal is healthy and safe, and cats have a lot of lives. So unsurprisingly, we call this and it says that this cat is safe, right? What's the best practice here then? Well, if you're designing a class hierarchy where there's any question as to what the best interface is for the people who will be using your class, add an accept method and a visitor type as a customization point. And that way, users of your class hierarchy can inject their own application-specific dynamic dispatch in it. There's another approach I'd like to talk to, which, two reasons. First, in a lot of ways, it provides the best of both worlds to both approached. And the second, it has a really good name, which is duck type variance, right? So, I don't know if you know what duck typing is, but it's a fairly simple idea. So there's a saying that says if something walks like a duck and it quacks like a duck, well, then it's a duck. Can we apply this principle to types? Well, inheritance models the notion of ISA. It's a way to model the object-oriented concept of ISA. But we're saying if something walks like a duck and quacks like a duck, then it is a duck. So maybe we don't have to look at the inheritance. We just have to look if it has a walk method and a quack method. And if it does, let's call it a duck. So inheritance, if you look in the literature, it's sometimes called nominal typing for this. And duck typing is called structural typing. It just supports the right operations. Now, templates have always used duck typing, So here I have a template for squaring x times x, right? And it doesn't require x to inherit from a has multiplication class for this to work. It'll work as long as I can multiply two x objects, right? Concepts improve the duck typing, like if we really wanted to catch in the signature that this only works for types that support multiplication, we could define a has multiplication concept and we wouldn't have to modify any of the classes we were using. So you could just very specifically fill out your requirements. Now, while C++ templates have always been duck typed, they also tie you to compile time types. And these are two things that you don't really want to stick together, right? Nominally typed versus structurally typed, and compile time versus runtime. So remember, we might have liked having that animal concept, but now we don't like that we can't create a sad animal to make a zoo, because we would need a common base class to give a consistent type to set. So because duck typing is flexible and forgiving while remaining statically type safe, people have asked whether we could use dynamically dispatched duck typing as an alternative to inheritance in virtual. And this is where variants come in. C++ is a lightweight variant abstraction that generalizes C unions. A variant AB can hold an A or a B, but not both, okay? So this will be more dynamic than having an animal concept because it can change at runtime whether it's holding an A or a B. And because everything's value-based, we don't need to worry about unique putter, object lifetimes, stuff like that. And the performance may be much better because we don't have to call the memory allocator. So, again, I'm not going to teach variants, but you use them similarly to tuples. Here, this variant int double v equals 3 holds an int now, and I can use get accessors to get them either by index or type. And if I put 3.5 in it, it now holds a double. So now we know all our classes at compile time because they're classes. You can't define them at runtime. So we can say animal is a variant cat dog. And now that's a great way to store either a cat or a dog. Now, how can I call the name method? Well, the C++ standard library is a solution for that called std_visit. Okay, it's just similar enough to the visitor pattern to be confusing. So I like to think of them separately. So if V is a variant and C is a callable, V visit calls C with whatever actual type is stored in V as an argument. And does this make variants behave like virtuals? Well, yes, it does. Our animal A is a variant cat dog. So if I visit it with a generic lambda that calls the name method, X will be either cat or dog because variant visit calls it with the actual type that's stored in there. And usually we encapsulate this in a helper function. And I have a godbolt for that as well. And you have to write the helper functions, but it doesn't look that bad. A name of A eats of A. How does it compare? Well, in some ways, it is the best of both worlds. Since animal's a single type that can hold a cat or dog, we can just use animals by value instead of having to do memory allocation and worry about memory management and lifetimes and stuff. There's no brittle inheritance hierarchy, but we maintain a reasonable level of static type safety. But it's also as dynamic as traditional inheritance virtual stuff because a sad animal works great. Animal is an actual type. It's not just a concepts. In fact, it even looks a little nicer than the other thing. Another thing is virtual functions. They're really, really picky about how you override them, right? So it turns out cats don't only eat mice, right? For example, they eat my toe. So what you'd like to do is if the eat method default its argument to being mouse, but let it eat other things. But you can't override with it because the signature has to be no arguments, even though you can call this one with no arguments. So you end up getting a lot of very tight coupling and brittleness with inheritance. But if we did the variant approach, all we're trying to do is call it with no arguments, and as long as that's legal, we're good. So this makes your programs more loosely coupled. Users can also add methods, right? Instead of using the visitor pattern, they use something called the overloaded pattern. And the overloaded pattern is absolutely great template about how sometimes these features in C++ work together like magic, right? So first thing we do is we define overloaded class template that just inherits from all its template arguments. And because of method hiding, we have to also have it pull in any function call operators in its template arguments. So this inherits the function call operator of everything it's constructed with. So here I can say overloaded hit points and give a lambda for hit points of a cat, a lambda for hit points of a dog. Class template argument deduction computes the template arguments as the types of these lambdas. It's a good thing because there is no name for the types of the lambda. But they're there, and now I say visit of hit points A, and that will get the hit points based on the runtime type. So the overloaded idiom is a great way for you to inject your own runtime dispatch methods in an external class hierarchy that you can't modify. Now, there are some problems with it. Notation's uglier than calling a virtual function, and while the flexibility is nice, it does slightly weaken type safety, right? A shapes draw method and a cowboys draw method are not the same thing. It's not always more efficient. It uses as much space as the biggest type. And whenever we create a new kind of animal, we have to add it to the variant and recompile the world, which can be challenging at production scale. So the best practice I have here is that because it's ugly and not well known, only prefer variant-based polymorphism over virtual or concepts when there's a clear benefit to doing so. Now in practice, I use it a lot, but less than I do virtual functions or concepts. And I have a little cheat sheet I keep in my head that says, what's the difference between all of them? Do they have a simple built-in notation? Well, virtuals and concepts do. Concepts and variants have the best performance. concepts are statically dispatched. They use the compile time type. The others are dispatched at runtime. Concepts and variants both support duck typing and value-based programming instead of putting things on the heap with references. And they all have their own method for client-side extensibility that we've covered. I didn't do it for concepts because it's for free with concepts, right? Add a method, it'll still satisfy the concepts. Now you may say, are there other techniques, right? In particular, you may be very familiar with things like static polymorphism or pre-C++ 20 template technique like SFIN-A and void-T. For the most part, those are mooted by the C++ 20 approaches that I've covered here, which are better. And if for legacy program or because you really need nominally type static dispatching, you know, you might need to learn static polymorphism at some point, but, you know, learn it when you need it. Now, I said for the most part, well, I did miss one, which is a technique called type erasure. We don't have time to cover it today, but it does deserve to be part of your toolkit. And depending on my mood, I think of it either as virtual functions with no base class or variants, even if you don't know all the types. But it requires a lot of complex boilerplate. So here's a great article, and here's a great talk by Rob Douglas on it. So thank you very much, and I think we have time for a few questions.
Thanks for your final table, but you should add which C++ standard, in which C++ standard you can use which feature, because not all of people can use 20.
Yeah, I put a note that sometimes you even need to use really ugly stuff like SFIN-A before C++ 20. So that table would be a lot bigger and a lot more complicated. You know, I like to live in the ideal world here, but you may need to learn other types for different standards. You're totally correct, and I acknowledge that.
So with the virtual inheritance, declaring something final, does that help with your example with the
the compiler will, if you declare something final, will be able to do additional optimization in the example I gave, but I don't think it really works in practice, because if there's really only one class, there's no purpose for declaring something final. So somewhere or other, there's going to be overriding, and sometimes you're going to access through a base class pointer.
But if say if you have just two, right? So you have one inheritance, then the last one is final, and that's the one you actually care about in lining, right? Would that do that or not?
Well, what if you're accessing it through a base class pointer? That base class pointer can't know what are all the possible things that inherit from it, right? That's the power of, you know, object-oriented dispatch for the user and the challenge for the implementation system. Nevertheless, I don't want to overstate the performance penalty of using virtuals. Usually it's very good, but if you're using it everywhere, I'd be, you know, it may do you some harm, and think about those polar bears.